Hello viewers, thank you for joining to this lesson. Our topic is circle theorems. Now in this lesson, we shall state and derive theorems and tackle questions touching on angle properties of a circle. Now our learning objectives, we expect students to apply the knowledge of circle properties to solving problems and identify and apply circle theorems. Now let's start with the first part on this, naming the parts of a circle, and we shall start with defining a circle. Now a circle is a set of points equidistant from its center. This is illustrated below. As you can see, we have the center of a circle, and now the distance around the outside of a circle is called circumference. So this is shown below in a yellow line, an orange line. Now let's talk about the radius as also another part of a circle. The radius is the distance from the center of the circle to the circumference. So that is our radius. And another concept is the diameter. Now, the diameter is the distance across the width of a circle through the center. So the diameter is shown in our diagram. And now let's move to arcs and sectors. Defining an arc is a part of the circumference, and on our diagram, the orange part shows the arc of this circle. This is the minor arc. Then when an arc is bounded by two radii, then a sector is formed. So as you can see, the region painted orange forms our sector, and it is bounded by two radii. And now, moving to angles in a circle, we shall start with right angles in a semicircle, or the angles formed by a semicircle inside a circle. Okay, the diagram below is a circle with 3 points on the circumference. That is A, B, C. And we have A and C to be the diameter of this circle. And so we can say that the angles formed by this diameter to the circumference of the circle in one segment is equivalent to 90 degrees. And that means that the angle in a semicircle is 90 degrees. And that is the concept of right angles in a semicircle. Now, right angles in a semicircle, so we want to prove that concept. We have just seen a demonstration that the angle in a semicircle is a right angle. Now we can prove this result as follows. So we are going to draw a line from C to O. As you can see, this line is radius of the circle. And now in a triangle AOC, we have that OA is equal to OC because they are both radius. So angle OAC is equal to angle OCA. You can see that. And that is because the angles at the base of an isosceles triangle, they are equal. Angles at the base of an isosceles triangle are equal. Now let's call this angles x. In the other part of the triangle BOC, OB is equal to OC. It is because they are both radius of this circle. And so the angle OBC is equal to angle OCB. Definitely it is because angles at the base of an isosceles triangle are equal. And now let's call this a y. Therefore, in triangle ABC, x, we can add all the angles. We can add all the angles because we have that sum of angles in a triangle add up to 180 degrees. So we have it that 2x plus 2y is equal to 180 degrees. And that means that x, if you simplify that, it means that x plus y is equal to 90 degrees. And so we have that angle ACB, which is x plus y is equal to 90 degrees. So let's now move to calculating the size of unknown angles. And we shall start with this question. Calculate the size of the labeled angles in the following diagram. And we have that our diagram is a circle. Is a circle with the center O, and we have the given angle 37 degrees, and then other angles are labeled with letters. And so we can find very fast, having known that A is equal to the other angle given 37 degrees is one of the base angles of a isosceles triangle. And we have that base angles of isosceles triangles are equal. So we have A and 37 degrees, they are the base angles of a isosceles triangle, and so they are equal. So we have A is equal to 37 degrees with the same reason. Now B will be 90 degrees minus 37 degrees, because we have that angles in a semicircle. So because A is equal to 37 degrees, and where we have B and A should be 90 degrees because of angle in a semicircle is equal to 90 degrees. So to get B, we subtract 90 minus, we take 90 minus 37, and so the angle at B is 53 degrees. Let's now find the value of C, having known that C and B happen to be the base angles of a isosceles triangle, So we have C also will be 53 degrees. And D, we have that C and B being the angles at the base of a isosceles triangle, and that angles in a triangle add up to 180 degrees. So we'll take 180 minus 53 plus 53, because they both happen to be in a triangle. So we want to find the other angle that makes it to be a triangle. And that will be the value of, now the angle at point D will be 74 degrees. And the last point is, the last angle here is E, which will apply the property angles on a line add up to 180 degrees. So you can also apply angles in a triangle add up to 180 degrees, because we have 37 degrees, and E and A, they are enclosed in a triangle, so that property can also lead you to finding the value of E. But very first, we can just pick angles on a line adding up to 180, that is 180 minus 74 degrees, so the value of the angle at point E is 106 degrees. Okay, the angle at the center is another property that we want to talk about. So we have it that the angle at the center is twice the angle at the circumference. So as you can see, we have the angle at point A with the angle 45 degrees, and we have also point D and point B. So an arc that is BD, subtends an angle 90 degrees at the center and an angle of 45 degrees at the circumference of this circle. And so we want to show proof for this. Now we have that we have just seen a demonstration that the angle at the center of a circle is twice the angle at the circumference. We can prove this result as follows. So draw a line from B through the center O and to the other side D. After that, considering triangle AOB, we have that OA is equal to OB because they are radius of this circle. So also we have OAB, the angle OAB, and angle OBA. These are angles at the base of a isosceles triangle, and so they are equal. We can call these angles X. Then we consider another triangle BOC, that is OB is equal to OC. Both of them are radius, so that means that OBC and OCB are equal angles at the base of a isosceles triangle formed. Now we can call these angles Y. So with that, we have it that angle AOD is equal to 2x and angle COD is equal to 2y. This is because the exterior angle in a triangle is equal to the sum of the opposite interior angles. And now angle AOC will be 2x plus 2y. So that one can factor out a 2. So we have it that angle ABC will be x plus y. Therefore, angle AOC is equal to 2 times angle ABC. So that means angle AOC is the angle at the center, and angle ABC is the angle at the circumference. Therefore, we can say that the angle at the center is twice the angle at the circumference of the same circle. Now, let's look at an example here. We have calculate the size of the labeled angles in the following diagram. So we have been given two angles, that is 29 degrees and 41, and the unknown angles labeled with the letters A, C, and D. Very first, we can say that A is equal to 29 degrees because of the base angles of isosceles triangles are equal. So let's find B. Because they are in the same triangle, so we can apply the property of angles in the same triangle, add up to 180 degrees. So that can give us 180 degrees minus 58 to get 122 degrees. Moving to C, we can relate C and B because we have that we can see C is the angle at the circumference of the circle and B is the angle at the center. So we have that angle at the center is twice angle on the circumference. That would mean 122 degrees divided by 2, and the value of angle C is 61 degrees. D, we will consider the bigger triangle. We'll consider the bigger triangle with angle C. With the other side we have D and 29 degrees, and the one on the right hand side we have 41 degrees and A. So if we add all those angles together, we'll get 180 degrees. So that means we can take 180 minus, if you add all the given angles that we have so far gotten, you will get 160 degrees. So 180 minus 160, the value of angle D remaining is 20 degrees, with the same reason of angles in a triangle adding up to 180 degrees. Well, now let's move to angles in the same segment. Angles in the same segment. And we have that angles in the same segment are equal, and we are going to show proof for this. We have just seen a demonstration on the angles in the same segment being equal. Now we can prove this result. And we have 4 points on the circumference of this circle, that is A, B, C, D. These 4 points can give us the chords. Like we have chord AD, we also have BC, and some others. Now, marking the center of the circle O and angle AOB. So that means we have AOB being the angle at the center, and then ADB being the angle on the circumference. Same applies to ACB. Now we have that angle ADB is half of angle AOB. That is true. Another one, we have angle ACB equal to a half of angle AOB. That is also true. and it is because the angle at the center of a circle is twice the angle at the circumference. Therefore, we can say that angle ADB is equal to angle ACB. That is very correct. And now, we can use the same concept of angles in the same segment to be able to calculate on the unknown angles in the diagram below. So in the diagram, as you can see, we have unknown angles C, D, A, and B. We have been given angles 51 degrees and 44 degrees. And so, very first, as you can see, with the center, the line passing through the center happens to be the diameter. The center is O. So that means you can recall the concept of right angles in a semicircle. So if we have, that means that the angle A will take, to find angle A, will take 90 degrees minus 51 degrees, and that will be 39 degrees. The reason remains to be angles in a semicircle is equal to 90 degrees. Then we can find B. So we have that to find B, we'll take 180 minus 90 plus 44, and that will give us 46 degrees, because it is, the property is angles in a triangle adding up to 180 degrees. So finding on C will be 46 degrees, and that is because of the property that says angles subtended by the same chord or arc are equal. So as you can see, we have C and B being on the same segment, and also we have said angles on the same segment are equal. So C will be 46 degrees. Let's work on D. D is the same concept. D will be 51 degrees because the property, you apply the property of angles in the same segment equal, they are equal. Again, you can also say angles subtended by the same chord in the same segment are equal. In the same segment are equal. Now, let's move to this concept of angles in a cyclic quadrilateral. In the diagram below, we have 4 points on the circumference of the circle. We have A, B, C, and D. And we have a quadrilateral, which seems to be a square. And so we can say that opposite angles in a cyclic quadrilateral add up to 180 degrees. So in this case, we mean B and D are opposite angles. Again, A and C are opposite angles. So we have just seen a demonstration that the opposite angles in a cyclic quadrilateral add up to 180 degrees. So we can prove for this result, and marking the center of the circle O, and label angles ABC and ADX as X and Y. So we have the angle at D has been labeled X, has been labeled Y, sorry, and the one at B labeled X with the center O. So the angles at the center are 2X and 2Y, because angle at B, that is X and Y, these are angles on the circumference of a circle. And given the center, so that means the angle that will be formed at the center, that angle will be twice the one on the circumference. And so this is what we are talking about. So this concept is because of the angle at the center of a circle equal being twice the angle at the circumference, sorry. So we have 2x plus 2y being equal to 360 degrees. So we can simplify this equation. So we have x plus y equal to 180 degrees. And so that is the concept of angles in a cyclic quadrilateral. We can also say that because of this theorem, we can conclude that the opposite angles of a quadrilateral add up to 180 degrees, and a circle can be drawn through each of its vertices. Now, the opposite angles in this quadrilateral add up to 180 degrees. So we have 113 degrees is opposite to 67. Then we have 109 opposite to 71. So that is a cyclic quadrilateral. That is a cyclic quadrilateral. And you are supposed to remember that when two angles add up to 180 degrees, they are often called supplementary angles. Angles adding up to 180 degrees. Now, let's solve on this question. Calculate the size of the labeled angles in the following diagram. So we have the unknown angles A, B, C, E, and D, with 33 and 128 the given angles. Now, A is equal to 64 because angle at the circumference, angle at the center is twice the one at the circumference. Now we can get the B and C, and we know that B and C, they happen to be the base angles of a isosceles triangle. So we shall get the supplement of 128, then divide by 2. So 180 minus 128, that will be 52, divided by 2 is 26. So both B and C will be 26 degrees each. Now on D, we have D and 33 being angles on the base angles of a isosceles triangle, meaning D is equal to 33 degrees. With the same reason, let's find D. So angles in a triangle, I think we have talked about this several times. Angles in a triangle add up to 180 degrees, so it will be 180 degrees minus 66, and that will be 114 degrees. Let's find on the last angle remaining, the angle F. And now this is where we apply the concept of cyclic quadrilateral. We have that opposite angles in a cyclic quadrilateral add up to 180 degrees. And in this concept, we have C and F opposite to E. So that means it will be, if you take C plus F plus E, you will get 180 degrees. So to get F, we'll take 180 degrees minus E plus C. That will be 140, and therefore the value of angle F is 40 degrees, with the same reason on opposite angles in a cyclic quadrilateral add up to 180 degrees. Now, our third part of the lesson, this is actually our last part of this lesson. We are going to talk about the tangent and the radius. The tangent and the radius. And it is proven that the angle between the tangent and the radius is 90 degrees at the point of contact. So where the radius of the circle meets with the tangent, at the point of contact on the circumference of that circle, it will be 90 degrees, or they meet at right angle. Now, we have two tangents from a point. So we have that two tangents from the same point to a circle are of equal length. They are of equal length. So as you can see, we have a PQ is one tangent. The other one is PR, also a tangent. And where these individual tangents meet with the radius, then that point of contact, the angle there will be 90 degrees, as we have talked about that. And so let's now look at the perpendicular from the center to a chord. So the property here is the perpendicular from the center of a circle to a chord bisect the chord. So as you can see, OC is the perpendicular height, and it is from the center of a circle, that is center O, to a chord, and the chord is AB. So that perpendicular length bisect the chord into two equal parts. Now let's move to the alternate segment theorem as our very last part of this lesson. The alternate segment theorem. Here we have a diagram of a circle and a triangle inside it. And as you can see, we have a tangent at point A, and also three chords, that is AC, AB, and BC. Now, we can say that the angle between a tangent and a chord is equal to the angle in the alternate segment, and that is what we can say to state on the alternate segment theorem. So as you can see, 68 is an angle formed by a tangent and chord AC. So that means that because from our statement, the angle between a tangent and a chord is equal to the angle in the alternate segment. So the alternate segment is A, that is the major segment, that is AB and C. ABC, that is a major segment, and so it will be equal to, that 68 is equal to the angle found by the chord in the other segment, that is the bigger segment, or rather major segment. So that's why you see the angle shaded green is equal to the other angle shaded green, because it is formed by a chord and a tangent, and the same chord forming this 68 is forming the other angle, or is forming an angle in the major segment, or in the alternate